So this is chapter 3 in Campbell biology. So we're going to go over water and how awesome it is for biology just in general. So when we talk about water, like you've talked about in your chemistry classes, water has very unique properties, and these are the unique properties you need to make sure you remember. These ones right here, and we're going to go through each of these properties on each slide. So the first property we're going to look at is this idea of water attraction. Now there's two different types of water attraction. There's cohesive forces and adhesive forces. The cohesive basically means that we're attracting water to more water. So water to more water. Okay? Whereas the adhesive forces is when you're attracting water to something else. So this co means basically the same as like joining together. So we're joining together two waters, whereas adhesive is like if glass collects on your surface, when it's a hot day and you got that cold ice glass of tea, it's going to collect water on the outside. Well, that's because of the adhesive forces. And then the surface tension is basically occurs because of the cohesive and adhesive forces. So if you've seen one of those little water striders, or also there's also those lizards. So if you have that water strider, and he is hanging out up here, and here's my bug, it's a fantastic bug, and he's hanging out up here on top of the water, basically because of the cohesive and adhesive forces, the water will not break in those areas. So he doesn't sink down. And so it allows for this. It's because of the surface tension, because of the water molecules are joining together. They're coming together, real locked together like this. But also there's the water. There's the water right here, and the lizard actually able to join together because of adhesive forces. The next property of water that makes it so good in biology is that the water's high specific heat. Now remember, specific heat is the amount of energy, so the amount of energy it takes the water to raise 1 degree Celsius. 1 gram of water to raise 1 degree of Celsius. So again, 1 gram of water to raise 1 gram of Celsius. So it takes a lot of energy for that to occur. So because of that, we can use water like things like heat sinks. A lot of times, let's say if we're growing a plant. So again, we're growing this plant. So we have this plant here. What we'll do is we will set up what's known as a heat sink. And essentially what a heat sink is some kind of vessel. And in this vessel, there will be water. Okay? And so we're growing this plant, and we want to see what's the effect of light on the production of photosynthesis, or the rate of photosynthesis. So we're going to put the light. So here's our light. We're going to put this light right here. We're going to put that light on the outside of the heat sink, on the outside of the water. So that way, the light will go through. So here's all the light going through towards the plant, allowing for photosynthesis to occur, but there's no heat transfer. And so it allows for a heat sink. And again, that's why it's always cooler in the coastal areas, because of the high specific heat of water. And going along with the high specific heat, it's also the heat of vaporization. And so more or less same idea, but heat of vaporization, again, this vaporization basically means for it to turn to vapor, going from liquid to gas, or actually the reverse cooling, known as evaporative cooling, which is going from gas to liquid. Now, it takes a lot of energy for that to occur, so that's the reason why if you have that pot of water and you want to make that pot of water start to boil and cause steam, it's going to take a lot of energy for it to. But then it's also going to take a lot of energy for that to cool down. So you're going to have to add a lot of ice cubes back into the water to start to cool it down, to start to make it. So again, these are the ice cubes coming back in the hot steaming water to make it cool back down and actually drop the temperature back from a gas to a liquid. So it's all because of heat vaporization, again, because of the high specific heat. Another property that allows for the human body, or for the biological body, to make it much more effective as a life organism, so it doesn't change its temperature a whole lot. The next idea is freezing. And so freezing, now the thing with water is most times something becomes solid. If you go from a liquid to a solid, it'll start to sink because it becomes more dense. That's basically the definition of a solid. A solid is merely just a liquid that has become more dense because of lack of energy. The difference is that when water becomes frozen, or it goes to a solid, it becomes less dense. So here's the key idea here, is that ice floats. Ice floats. Unlike anything else, ice floats. And it's because of, and I haven't talked to you about this yet, but all of these are because of something called hydrogen bonding. And so the hydrogen bonding, if you ever get a question about water, if you throw this idea of hydrogen bonding in, you'll get a point. I mean, it's almost guaranteed there'll be a point. You're going to get at least partial credit, and so always make sure that you use the term hydrogen bonding. Okay, so let me explain here what that is. Let me give you a clean slide. So here's what hydrogen bonding is. So we have our oxygen here, our hydrogen here, your standard Mickey Mouse water. And again, oxygen here and hydrogen here. Now, what that says is that basically, remember, oxygen is a negatively charged or partially negative in water, and hydrogen is partially positive. Same thing here, partially negative and partially positive. Now what happens is, because this is positive and that's negative, what you end up getting is something called a hydrogen bond. And a hydrogen bond is basically a very weak attractive force between the positives and the negatives. So this positive hydrogen is going to be attracted to this negative oxygen, and you have another one. Now if there's another oxygen up here, again you have another negative oxygen up here, this hydrogen is going to connect to that. And so again you have another oxygen up here, this hydrogen is going to connect to that. And so what you end up having is this dead space. Now I'm going to show you the dead space. So this dead space right here in this purple area, this is all air. And so this only occurs in water because of its polarity. So the two things you need to remember about water. If you are completely stuck and you're supposed to be writing about water and you have no clue what to write, all you have to write is this idea of hydrogen bonding. And why is it hydrogen bond? Well, because again, water is polar. And because of the polarity, and because of the hydrogen bonding here, it creates this dead space. So here's all this dead space. This is all air. And if you have something with a lot of air, like if you have a balloon, it floats. If you have a lot of air in a ship, it floats. It's because of that air that water floats. And so things like in the lakes, the fish don't die in the wintertime, because in the wintertime, the water all freezes to the top, it insulates us like a gigantic blanket, and the fish don't die because they go to the bottom. It's because of the hydrogen bonding and because of the polarity. The final idea here is universal solvent. So again, we have the polarity, we have the hydrogen bonding, and again, the reason for that, or the reason again for this universal solvent is because of the polarity, and the polarity causes hydrogen bonding. So the polarity causes hydrogen bonding. Okay, so this hydrogen bond, polarity, and so again, if you don't remember, a solution is that is a mixture of both the solvent and the solute to make a solution. The solvent is what's doing the dissolving. So again, this is the one that's doing the dissolving. That's why water is known as a universal solvent. And the solvent is the one that's doing the dissolve, is being dissolved. So again, the water is doing the dissolving, so it's known as a universal solvent, and the solute is the one that is being dissolved. So if you're making salt water, the reason why salt water is made so easily, the reason why we use water to make solutions, is primarily because of its polarity. Its polarity is used as a magnet. So if you're making salt water, the sodium chloride, which is the Na plus, and the Cl minus, the polarity, the positive oxygen, the positive hydrogen will pull away the negative chlorine, and the negative hydrogen will pull away the positive sodium, and so basically it's like a magnet. So anything that is polar will be dissolved by water. And so again, this is again this idea of hydrophobic and hydrophilic. The term philic actually comes from the Latin term philus, which is from our friend or brother, and then phobic is the term of phobia, so to fear. So hydrophilic is water loving, and hydrophobic is water fearing. And the final idea, again, with acids and bases from the solutions, is that, remember that solutions are made with, their acids and bases are normally solutions, but first off, that there's the pH scale. So it goes from 0 to 14, with 7 being in the middle, 7 being water, which is neutral, distilled water being neutral. And the further you get over to here to 0, the further you get to 14, the more caustic these acids and bases become. Now, a lot of times people use these terms strong and weak acid. And they normally use it to say, well, this acid is a pH of 2, and so it's a super strong acid. That's not exactly true. If it's a pH of 2 and it doesn't dissociate completely, it's still technically a weak acid, but it's not, it might be as caustic, but it's weak. And so what weak means is that it doesn't dissociate completely. The ions that make up the acid don't pull apart completely when put in water. Same thing with the base. If the base is put in water and it doesn't dissociate completely, it doesn't separate out completely, then it's not a strong base. It's still a weak base, even though it might be higher on the pH scale. That being said, most biological fluids are between 6 and 8. So it's going to be right near the neutral range. So we're going to kind of talk about this area right around here. So most biological fluids are going to be between the pH of 6 and 8. Well, what happens if you get sick and your kidneys aren't working very well, and you start raising, your endocrine system isn't working, and your pH starts dropping lower and lower? Well, that's why we have things called buffers. And buffers are super important. If you don't have a buffer, your body gets super sick, mainly because a buffer reduces the effect of acid on your body. So you need a buffer, and we'll use buffers in solutions to lower or to raise the pH and keep the pH about the same. And then finally, this ability to calculate differences in pH values. Remember, pH is on a logarithmic scale. So if it goes from a pH of 5 up to a pH of 6, it actually is decreasing by 10-fold. So, and I will give you the formula for that whenever we get to that point. And finally, when we talk about biology and acid and bases and those kind of things, we always have to make sure that we start looking at what is the effect of acid precipitation. So the lowest recorded acid precipitation is 1.5. And remember that our acids in our body go from 6 to 8. So if you're a fish swimming in the water in this pond, and you have your little fishy here, and this fish, it's a big tail, this fish is in a lake that's 1.5, that fish is dead. It's not going to survive because no buffer will actually keep it surviving. And remember, acid rain is because of most of the time of some form of pollution in the air that mixes with the sulfur dioxide and the nitrogen dioxide that's mixed in with the water that's in the air because mostly of burning fossil fuels. So again, that's another reason why we always talk about cleaning up our abs and clean up where we're at. Anytime it's below 5, it can't support life. So just remember that. The key idea right there is that it's below 5, it can't support life, and that's because it's combining with the fossil fuels to form water. So I hope this helps you look at water and make sure you take your notes and put your recording and your comments down below. If you have any questions, ask me in class, or you can email me back. Thanks for watching.